Hello students, now we are going to talk about the Ford-Fulkerson algorithm to find the maximum flow that is possible from the source vertex S here to the sink vertex or the destination D. So you will be given what is called a graph like this with the edges and the weights on these edges indicating the capacity of those edges. So that's the kind of the maximum amount of flow you can send from one node to the other node on this edge. So you can send 7 units of flow here, 5 units of flow from 1 to D, and so on. Now, so you see there are several paths from the source to destination, and each of these paths have what is called a bottleneck edge. The bottleneck edge is the edge that has a minimum capacity on that path. Okay, so for example, on this path from S to D going through S1D, you could send 7 units of flow from S to 1, but you see you can send only 5 units of flow from 1 to D. So if you use this path from S to D going through 1, you can actually send only 5 units of flow on this path, right? So on this edge you can really send 5 units of flow when you send something on this path using these two edges. So each path has a bottleneck edge. So we'll go through iterations in this algorithm, and in each iteration we'll try to saturate at least one edge on the graph. Saturate means use all its capacity. Alright, so the way we construct the residual graph is a graph that we will use to in each iteration to find the flow that is possible on that graph. Okay, so the way we consider the residual graph is like this. So if there is an edge in the original graph like this from say a vertex U to a vertex V of capacity say 3, then the edge that is represented residual graph like this. So there's no flow at on this edge from U to V, so the flow is 0 and the capacity is available capacity, which is in this case 3, and also there is a backward edge. So this is the edge that you really have, but you also want to incorporate a back edge, because once you start sending some units of flow in this direction, there is an opposite flow possible in this direction with a negative sign. So the formula to calculate the actually it is in this here, let me right. So the once you find whatever you want to send, the minimum bottleneck edge capacity that you have, then the flow from U to V is actually added to whatever you have. The flow you add whatever you want to send now, and the capacity of the edge in the residual graph is what are the capacity initially before sending the flow minus what are the flow you're sending. So these two are in the forward direction. Now in the reverse direction, the flow that you have from V to U is the flow that you had before from V to U minus the capacity that the flow that you are sending. Similarly, the capacity of the edge in the reverse direction is the capacity of the edge before the flow minus this flow. So always the new capacity is the old capacity or the previous capacity minus the flow you are sending in that direction. Alright, so let's do this now. So this is how you construct the residual graph. So for this, for example, this edge from S to 3 of capacity 2, initially it is 0/2 in this direction, and in this reverse direction it is 0/0, and so on. Okay. Now, so in each iteration you will be finding a path from the source S to the destination D. So to start with, you will say, let's say you can pick any path you want. You can actually, when you implement it, you can actually run say a breadth first search algorithm to find a path. So let's say I chose S to D as the path, and you see that this has a bottleneck edge of capacity 3, right? So this is the maximum you can send on this edge from S2 to D. So which means on this edge from S to 2 you can increase the flow by 3 units. So that bottleneck edge capacity you found is 3, and you can increase that on both these edges. So this is 3, so the capacity on this reduces from 8 to 5. 8 minus 3 is 5, and you're saturating this edge, so the flow is now 3 and the available capacity is now 3 minus 3, which is 0. And on the reverse direction, in each case, you see the flow is actually 0 minus whatever you're sending. So 0 minus 3 is negative 3. And the formula for the residual capacity is what? Whatever the capacity you are sending, right? So the formula for the residual capacity in each direction is what? The capacity before the flow or after the flow is going to be capacity before the flow minus the flow sent. So in the reverse direction, the capacity before the flow is 0 minus the flow sent is negative 3, so that's why it is plus 3 in this direction. You see, this is plus 3. Similarly, in this direction, it was again 0, right? So 0 minus again negative 3 is the flow, so that is still equals 3. Okay, so in each edge, backward edge, it's set like this. So now on this graph, okay, so what is the flow that you have sent now? 3. So we have to note down how much you are sending on each iteration. So in this iteration, we have sent 3 units of flow. So now continue. So on this graph, find another path from S to D. So let's say I use this path S to 4D. So this the bottleneck edge capacity is 5, 4, 6. So the minimum among this is 4. So basically you can increase your flow here from 3 to 7. 3 plus 4 is 7, and you're using 4 units of capacity on this. So 5 minus 4 is 1, and you're increasing the flow from 0 to 4, which is 4, and 4 minus 4, the available capacity is 0 now, and then 0 to 4, then 6 minus 4 is 2. On the reverse direction, you have already negative 3 minus the 4, so it's negative 7, and again like 3 minus minus 4, like what we have right now in that edge is 3 minus minus 4, so that makes it to be 7. Okay, so that's what it is, this, and then minus 4, negative 4, 4, and then negative 4, 4 on this direction. So the flow that you are sending in this graph is going to be 4 units. Okay, so now on this residual graph, find another path if one exists, and there is one here, which is this. You can go from S to 3, 3 to 4, and you still have 2 units of flow capacity available, so you can use this H4 to D. So the bottleneck edge is going to be here. You have 2, 3, and 2, so the minimum of this is you have 2 2's here, so that 2 becomes a bottleneck. So you can send 2 units of flow and saturate this edge, send 2 units of flow and reduce this from 3 to 1, and then saturate this edge 2. So this becomes like 2/0, and then opposite negative 2/2, and then 2/1, because you have sent 2 units of flow, and then there's only 1 unit of flow that is still remaining, and then it is 4/2, so that is you're increasing by 2 more units, so 6/0, right? So now on this graph, you find another path, which is this one, S1 to D, and the bottleneck edge is of capacity 5, so you're sending 5 units of flow, so this increases from 0 to 5. 7 minus 5 is going to be 2, and then this you're sending 5 units of flow, so it is 5/0, and in the reverse direction, the edge weight is going to be the flow is negative 5/5, and then negative /5/5. So you see now we have sent 5 units of flow here, which is this, and then in the previous cases you sent what, 3 units of flow on this, 4 units of flow on this, and 2 units of flow on this. So you add up all the flows that you sent in each of those iterations, that gives you the maximum flow that you can send from the source to the sink. Okay, so now if you kind of remove all those back edges with a negative flow, basically you get a graph like this, and you see some of the edges are saturated, the ones that have 0 available capacity, right? So now if you look at this final flow graph, you see from S you could reach some of the other vertices, and you cannot reach some other vertices. For example, from S you can reach 1 through this edge because it still has an available capacity of 2. Similarly, you can reach from S to 2 through this edge because it has an available capacity of 1. Whereas you cannot reach from S to 3 because this edge has a available capacity of 0. Okay, so you cannot use that edge anymore. Similarly, from S to, you can come from S to 2, but from 2 you cannot go to 4, right, because this edge is saturated. Similarly, you cannot go from S to 3, so you cannot reach 4 from 3. So basically from S you cannot reach 4, so S and 4 are disconnected. With the same thing, you cannot reach from S to D because you cannot go from 4 to D, you cannot go from 2 to D, and you cannot go from 1 to D. So all the edges leading to D are saturated here, right? So you cannot really go from S to D. Alright, so you have to either go through like this, S to 1, but you cannot go from 1 to D. If you go through like this, you cannot go from 2 to D, or you cannot go this way, and you cannot go from S to 3. So S and D are disconnected, as well as S and 3, as well as S and 4 are disconnected. So I can come up with a set of vertices like S1, 2, S is reachable from it to itself, and S is reachable to 1, S is reachable to 2. So these are one set of vertices, and S is not reachable to 3, 4, and D. So now if I try to find in the original graph all those edges that connect any vertex in this set S that is reachable from S and this set T that is not reachable from S, then we can come up with these 4 edges if you look at this original graph given to you, right? So from S to 3 you have this edge weight H2, from 2 to 4 you have 4, and then what else? From 1 to D you have 5, and then from what else you have? 2 to D you have 3. So all these 4 edges on this graph, all these 4 edges, this is between S and T, and this is S and T, and this is S and T. So these 4 edges constitute what is called the minimal cut, which means if I want to disconnect S and D from in the original graph that is given to us, then I have to remove these 4 edges, right? And only if I remove all these 4 edges, S and D are disconnected. If I even leave one of these 4 edges in the graph along with the other edges, then the graph will be connected between S and D. Okay, so if I want to disconnect S and D in the original graph, I have to remove these 4 edges. So with this Ford-Fulkerson algorithm, what you really solve is 2 things. You're finding the maximum flow from the source to the sink, S to D, as well as you're finding what is called the minimum number of edges to disconnect the source and the sink. So that's why this is called a max flow min cut problem, and the theorem is basically telling you that once you solve the graph using the Ford-Fulkerson algorithm, what you're finding is the max flow from the source to the sink, and the minimum cut, indicating the minimum set of edges that you need to use to remove or disconnect the source and the destination, which is a sink. Okay, actually we can prove this. We are not going to see that in this course, right? Okay.